Hello and welcome to this video. This is an optional video, so you don't necessarily have to watch it. But hopefully this example problem will prove useful to you as you're thinking about how we're using some of the different equations that we've been deriving in class. We've been kind of getting a little bit equation heavy. In this video, I hope to connect them back to things that you already know how to solve, like a Brayton cycle. So that's what we're going to do in this video, is we're going to solve a Brayton cycle. But now, instead of looking up all the values in, say, cat3 or something like that, we're just going to be going through and calculating them from some basic kind of first principles type things like we've been doing in class. So here's the system. It's a system that we've actually solved before. We have a Brayton cycle that looks like this. Schematic here. It has 100 megawatts of total power. Again, this is a system that we've solved before. The exhaust of the turbine is at 100 kPa. The inlet to the turbine is 1.5 megapascals and 1500 C. We're going to assume that nitrogen is behaving as an ideal gas and that we have this value of the constant pressure heat capacity, CP, 1.17 kilojoules per kilogram. And we have a few basic questions that we're going to be asked. Again, the same questions that we were asked in the homework when we solved this problem previously. That was on homework, the homework from week 9. Okay, what is the temperature of the nitrogen? What is the thermal efficiency of the cycle? And what is the mass flow rate of nitrogen? So we're going to write down just what our material properties are. So the heat capacity, this is something that we were given. The heat capacity, the constant pressure heat capacity is 1.17 kilojoules per kilogram Kelvin. Our value for R, again, this is something we could look up. It's R bar, the universal gas constant, divided by the molecular weight. And for nitrogen, this is 0.2968 kilojoules per kilogram Kelvin. We're also going to use this value K, which is the ratio of the two heat capacities, Cp and Cv. So this is equal to Cp divided by Cp minus R. If you remember the thing that we had, Cp equals Cv plus R for ideal gases. So we can use that same relation to determine this, and we can determine what our K value is. If we plug in numbers, right, 1.17 divided by 1.17 minus 0.2968, we would get a K value of 1.34. Right, K doesn't have units. It's a unitless ratio of the two heat capacities. Once we have those, we can actually start to run through the different calculations that we have. So the first thing, we're going to find the temperature of the turbine exhaust. So if we go back up to our cycle, we're looking at jumping over this process, over the turbine, from 3 to 4. We know our inlet state, 1.5 megapascals, 1500 C, and we know our outlet pressure. We also know something about this process, right? This process from 3 to 4 is a delta S equals 0 process. This is adiabatic and reversible. Okay, so process 3-4, adiabatic and reversible. What that means is that's a delta S equals 0 process. So for a delta S equals 0 process, we have relations between the temperatures and the pressures that were derived from looking at what's happening to entropy over that process. So T4 over T3 equals P4 divided by P3 to the K minus 1 over K power. We can then plug in our values for that and solve for our unknown temperature. T4 is going to be equal to T3 times 100 kPa divided by 1500 kPa to the 1.34 minus 1 over 1.34 power. Just a note, we need to use T in Kelvin when using entropy. So this is an important note. If we're using entropy, if we're using an equation that came from delta S, we have to use our temperature in Kelvin. So T3 equals 1,500, C equals 1773 Kelvin. And if we went through and solved this, we would find that our outlet temperature, T4, equals 892 Kelvin. There's our answer to part A. If we want to find the thermal efficiency, we have a couple steps, right? Our general equation is this guy right here, that the thermal efficiency is the net work divided by QH. We have a couple different work terms. We have WT, WC, and QH. We need to find all of these, so we'll start with the work of the compressor. Right, we're going to find these by energy balances. So our energy balance is delta H equals Q minus W. It's an adiabatic compressor, so that's 0. So minus WC equals delta H. And we can find delta H from Cp delta T if Cp is a constant, which we're saying that it is to simplify our lives. So now really we only have to find the temperature. Okay, so we know this is a delta S equals 0 process. So we can use some of these equations to find our, if we know the pressures and we know temperature, we can relate pressures and temperatures across a delta S equals 0 process using an equation like this. T2 over T1 is equal to P2 over P1, right? The exact same equation we just used, K minus 1 over K. We can plug in our temperatures. Again, we're going to be using temperatures in Kelvin. So T2 equals 293 Kelvin. That would be our inlet temperature of 20 degrees Celsius times the ratio of our pressures, 1500 kPa divided by 100 kPa. And then this function, K minus 1, so 1.34 minus 1 over 1.34. We get that T2 equals 582 Kelvin. And then we can find, right, minus WC equals Cp equals delta H equals Cp delta T equals, what was our heat capacity? It was 1.17 kilojoules per kilogram Kelvin times our delta temperature, which is 582 K minus 293 K. And we get that WC equals negative 338.6 kilojoules per kilogram. So that's our first step. Now we have to do a similar type of thing to find QH. QH is actually really easy. Right, we're going to use the same energy balance equals Q minus W. But now W equals 0. So we just get that delta H equals Q. And we know that for constant heat capacities, delta H equals Cp delta T, 1.17 kilojoules per kilogram Kelvin. And we already know what the difference in temperatures are because we calculated T2. This is now 1773 Kelvin. That's T3 minus T2, 582 Kelvin. So Q is going to be equal to 1393 kilojoules per kilogram. Our last step is to find the work across the turbine. We already know our temperatures across the turbine because we calculated that in part A. Our energy balance is the same energy balance. Delta H equals Q minus W. Q equals 0. So WT minus WT equals delta H. Delta H equals Cp delta T, which is 1.17 kilojoules per kilogram Kelvin, times our change in temperature, which is 892 Kelvin, right? That's the outlet temperature of our turbine minus the inlet temperature, 1773 Kelvin or 1500 Celsius. This gives us a delta H of 1,000 of negative 1,031 kilojoules per kilogram. So WT equals minus delta H. So the work from our turbine is equal to 1,031 kilojoules per kilogram. Okay, what were we actually asked for this problem? We were asked to find the thermal efficiency. Thermal efficiency is net work, right? What we want over what we had to put in. So the net work that we're getting out divided by the heat that we had to put in. So our thermal efficiency is equal to our net work, that's the turbine, 1,031 kilojoules per kilogram, minus the work that we had to put into our compressor. So that's minus 338.6 kilojoules per kilogram, divided by the heat that we had to put in, which was 1393 kilojoules per kilogram. And if we plug those numbers and run that calculation, we get a thermal efficiency of 0.497. Last question. Again, this is a question that we were asked before. If we have a network of 100 megawatts, that's 100,000 kilojoules per second. And that equals the mass flow rate times the net work, which is the work that we're getting from our turbine, 1,031 kilojoules per kilogram, minus the work that we had to put into our compressor, 338.6. And if we run those numbers, we get a mass flow rate of, I believe it's 144.5, not kilojoules. That's a mass flow rate, kilograms per second. So the problem-solving process looks a little bit different in this than maybe what we're used to when we were just looking up values. But basically it's still the same. We're still using energy balances. Right? We're still using the same energy balances. We're using things that we know about the process to be able to figure out, what's coming out the other end. In this case, we're using, equations like what I have circled here. That gives us the information about the process to figure out, the state that's at the final end. And then instead of looking up delta H, we're calculating it by a heat capacity and temperature. Hopefully this gives you a little bit of a sense of how we can actually use some of these things in solving problems in more complex situations like some of these thermodynamic cycles that we have done in the past.